Bismillahirrahmanirrahim. So let us move to the question 4. They say that the figure below shows a ray of light that moves from air through glass into water. So having how many media? We're having air, glass, water, 3 media, right? Given that the refractive indices of air, glass, and water are respectively 1.00, 1.50, and 1.33, determine the values of the angles lambda and theta is a phi. Determine the range of angles of lambda for which the ray of light entering water from glass still will completely turn back into glass. State one application of the phenomenon in B above. 1 mark. Okay, let us begin. So this question is just based on Snell's law, Descartes Snell's. So now applying Descartes Snell's. Snell's law says that n. Where's my pen? So Snell's law says that n1 sine I equals to n2 sine r. That is where n1 is the refractive index of the medium where the ray is being incident, and sine I is the sine of the angle of incident, which is the angle with respect to the normal. So let me just go ahead and put here normal. This is the normal. This perpendicular line to the surface is what we call the normal. Sine of incident, the angle with respect to the normal, is equals to n2, which is the refractive index of the second medium, and sine of the n2, which is the refractive index of the second medium, and sine of r, which is the refracted angle of refraction, which is the angle between the refracted ray and the normal. Okay, now let us go ahead and simply apply and see. So I've just simply applied not to waste much of your time. So we now have here, so the angle we need is the angle between this normal, not the 44 degrees. So we need the angle beta. You see these two things are perpendicular to each other. So beta will be what? 90 minus 44. Right, that will be beta. Now alpha is the angle of refraction. The angle at the line, at the radius enter the medium is alpha. They did not put alpha there, but the alpha is the angle that is supposed to be here, alpha, but it is not indicated. But now you have to know that from the angles of alternate angles says that this angle alpha is equal to the angle lambda. So finding alpha is same as finding lambda, right? Now if we go ahead and apply this Descartes Snell's, we just get that our n of a, where the first n1 is n of a, sine of I, which is now beta, is equals to n prime, or n is equals to n of water. N of water is it water? It is moving from air to glass. N of glass here should be glass. Sorry. N of glass into sine alpha. So we have 1.00 sine of 90 minus 44 equals 1.5 sine of alpha, where now alpha equals lambda. So I can put here lambda equals lambda. So I can put now here that alpha equals lambda. So now I just get that. So we just simply look for lambda here. You substitute this value, I got that. Please stop rounding from here. Avoid rounding. You end up having sine of something greater than 1. Always avoid rounding up, please. So you just substitute, you put, and you just get lambda to be sine inverse of this, and I got 28.7 degrees. So that is the value for the lambda. Now if we move to find the value of theta, anyway, let me just find it for you. Theta, now we are now moving from this. So our angle of incident with the normal is now lambda, and our angle of refraction is now theta. So you can now do it right. So you now say that n of glass into sine of our lambda have to be equals to n of water into our sine of theta. You still apply it like that. I just simply substitute. So this one is a assignment for you. So you just apply the same thing and you find it. Now that's telling us that to find the angle of, we should determine the angle of lambda for which the ray of light entering water from glass will completely go back to glass. So we are not talking a ray will leave this way and go back this way. That will only happen is if the angle of incident, the coming angle, is greater than what? The critical angle. And the critical angle is the angle of incident. Critical angle is the angle of incident when the angle of refraction is 90 degrees to the normal, right? That is 90 degrees here. So if the angle is just slightly greater than this, then the light ray will just be reflected back into air into glass. Into glass. So this is what I've written here. Total internal reflection to occur, incident angle hence have to be greater than the critical angle, and light must be moving from a denser medium to a less dense medium. Voila, very important. So we are having 1.55 for the glass, which is greater than 1.33. So hence there will be a time where, or a certain instant, that we will have total internal reflection. If not, we cannot have it unless these two conditions are satisfied. That is, it should be moving from a denser medium, the one with more density, to a less dense medium, the one with a less density. This is so because sine have to be greater than 1. If you apply the reverse, you get sine which is greater than 1, and that is wrong. Okay, let us go ahead and substitute. So now we are saying that our n of a sine of critical angle here have to be equal to n of water sine of 90 degrees. I say critical angle, now make critical angle the subject. We know that sine 90 is 1, so you just be sine inverse of n of water under n of a. I got the critical angle to be 62.5 degrees. Now, how do you just look at it here? I'm saying that sine inverse of 1.3 on 1.5, all that times sine of 90. Sine of 90 is already 1, so we can eliminate this term. And now we're looking for a critical angle. If the critical angle is this, is the opposite, that is, it is moving from a less dense medium, it will be 1.5 all on 1.33. And 1.5, I can just keep it to be 15. It will be sine inverse of 15 over 10. Let me put 150 over 100, dividing by 133 over 100. Right, and this one now will simply be sine inverse of 150 on sine inverse of 150 on 100 times 100 over 133, and this one goes 150 on 133 is greater than 1, and the sine inverse of that will give you error. Have you seen? The sine inverse of that will give you error, or we are saying that critical angle is equals to sine inverse of 1, which is showing you error in your calculator. So the two conditions are that the angle of incidence must be greater than critical angle, and the critical angle is the angle of incidence when the angle of refraction is 90 degrees. Hence, if lambda is greater than the critical angle, which is 62.5 degrees, then we have total internal reflection, not refraction again, because it is going back to the same medium. We call it reflection. Okay, now where is this thing applied? So we used it in telecommunication to transfer signals within an optical fiber. That is, it goes from fiber. I think we have done communication, something like that. Thanks for watching and have a great day. I wish you the best, and this is the last paper we are going to revise together. I think we are together, and don't forget us. When you go to university, we are still your seniors. We remain to help you. Have a nice day.